Okay, so part two, the CLEARSY Safety Platform for Education. So just to remind you that we just have to develop the F function using B. So for this demonstration presentation, we need to have SK0. So it's a starter kit 0 board that is optional because you can also play with a software simulator, a USB cable, a laptop, 2 switches, and the IDE. Again, you can download it, and you have the install procedure coming with it. So it's a zip file. So you just unzip in any directory with no space, no character, special character. Yes, it's Windows only. Sorry, so sorry Linux, sorry Mac OS. It's just for Windows. You have to do 2 things to run the script register cssp.tmd script, and it modifies the registry for you, and it creates a new command, startab.tmd. This is a script, and if you execute it, you get the window you get on the right. So it's self-sufficient. You don't need to install anything else. And it comes with 2 examples, clock and combinatorial, that you can have a look. And usually with the CLEARSY Safety Platform for Education, so it generates a skeleton project for you, so you don't have to write a B project from scratch. Usually you have to modify 2 components to prove, to compile, to upload, and to execute on the board, or just to execute on the software simulator. So the development cycle is again, it's straightforward. You create a CSSP software project, you configure the board, so you need to define which inputs and outputs are used and to provide them a naming. From this naming, the skeleton project is generated with the naming corresponding to the variables that are used in your model. You define the constants of your project, and you define the behavior in the logic component. So we'll see later on a concrete example: prove, compile, upload, and execute. Yeah, so just, a component in B just means a specification and its implementation. And this is what is represented here. So when you create a project, you get this picture. So all the boxes represent one component. So on the left, you have the interface with the safety library. So it contains types, it contains constants, it contains operation functions that you can use in your model. And on the right, you have user components, you have inputs, logic outputs. So this is where you program your transfer function F. And more precisely, the green boxes have to be modified. So user context and logic. So the user component is, so you can see what is being called all the time, user app. So you have read inputs, user logic, write outputs. The read inputs component is generated from your naming. So you get the operation that allow to get access to the values. So the syntax is PP, you have an arrow FF of V on the top right. It represents a call to the operation FF of VV that returns the value PP. Okay, so read input is generated for you, write output is generated for you. And in the component logic, so you just have to replace skip, that is do nothing for the user logic, by your own code. So some other modeling elements before we go for the example. So we have we can use a number of predefined typing elements. So you have assigned it on 8, 16, and 32 bits. The inputs outputs are digital, but it's not coded on 0 and 1 because the modification of 0 into 1 is too easy. So we have defined on 8 bits 2 values far enough from the other to avoid to have, with the modification of 1 bit, the modification of the state from 1 to the other state. So we have IO off and IO on that are the valid state for the inputs and outputs. And if you try to use other values to value an output, you get a panic, but we'll see this later on. We have a number of predefined arithmetic and bitwise operations. So, for example, add unit 8 computes the addition of two unsigned on 8-bit without overflow. And one of the specific of the language is when you have local variables, you need to type them with a predicate. Yeah, it's a function write outputs. Yeah, the local variable is LSB, and we just say, so it has no effect, just to provide some information to the code generator, and you just say that LSB is unsigned of coded on 8 bits. So two other slides before we go to the example. One is about the variables declaration. So I told you that we have a component is made of a specification and implementation. So implementation is what you know, what you use every day. If you program, if you are a software developer, so it's something concrete. You are using concrete types. At the specification level, you can use things more abstract. So you need to provide a name, you need to provide a type, and you need to provide a first value initialization. And in this case, we can see that we can use a specification where we can say that it's any value and it's double. For the operation, same thing. We have the specification, we have the implementation, and what is well seen is not to copy paste the code into specification, because in this case you just prove the quality of your copy paste. So usually we just write the post condition of your code. So what are the final values or the properties of your variables once the operation has been executed. So for example, here we just say that for user logic, O0, O1 are being modified, such as O0 is still inside it, O1 as well, and the two values are different. So you do not provide hints about the values they will contain, but you just say that the values will be different. And for the implementation, so you can say do nothing, meaning that you modify nothing. It can be variations in sequence. You can use if then else. You can use local variables declarations we have already seen, and operation calls. Okay, so now an example of a complete path from modeling to execution. Yeah. So you create a project. So you give a name, you select software development and define as a CSSP project. You define a board. So for the board here, we need to have two inputs, the announcement pedal and the free pedal. We don't need the other one, so we uncheck it. And for the outputs, we have two outputs, eng for the engine of the barrier and sig for the signal. We create it. And the project is generated for you. So everything is red at the moment because nothing has been verified. So we go for the specification logic. So we first need to add the counter that we will modify depending on the number of axons. We give it a type, so it's inside it on 8 bits, and initial value that is 0. We save it, and you can see that it's green because everything has been proved automatically. Now we modify the specification. Here we say that the three variables are going to be modified, such as you have only two possibilities. Either the engine is off and the signal is on, or the engine is on and the signal is off. And if the counter is equal to 0, then the engine is on, the barrel is up, and the signal is off. It was for the specification. Now for the implementation, so we need counter, but we also need to store somewhere the previous value for the announcement pedal and for the free pedal. So we are going to add three variables. They are initialized to 0 for the counter and off So the lower state for the two enhancement pedal, and the logic it's a bit more complicated. So we are going to have a look at this. So first, you remember that we have local variables. We need to provide a type. So this is a predicate we have seen already. And then we call the getAn function, which returns the status of the enhancement pedal and the status of the freeing pedal. If the previous value of the enhancement pedal is off, so it's 0, and the current one is 1, so we have a rising edge. And so we increase the counter using this predefined function, which performs an addition, counter plus 1 with no overflow. And in the case of the freeing pedal, if the previous version is off, so it's 0, and the current one is 1, we have a rising edge, so we have a train axle leaving the area. So we subtract 1 to the counter. We save the value of the pedals. If the counter is equal to 0, so we activate the engine, so the barrier is on, is up, and the signal is off. And if different from 0, then so we remove energy from the engine, so the barrier is going down, and we light on the signal. We select all the components. We start the proof, automatic proof. So you can see it's a real time. The time has not been compressed, and all the boxes are turning green. And if we check the status of the project, we can see that all the components have been proved. So everything is 100%. And now we can program, so different view, we can program the board. So you can see the board. I just selected the menu, which allows me to program. So you remember the two different chains. So I can activate the two chains with just one button. So you can see the carousel showing that everything was perfect. Now I just reboot my board. It's plugged on the USB cable and it's programmed. So you can see the light flashing. And when the programming is over, you will see a green checkbox on the upload step on the screen. Yeah, so you need to reset again to start executing the program that was uploaded. And then I will play with my, so I have switches, and I will play with my inputs. And you can see that the outputs have been modified accordingly. So there is a train entering. So the barrier is off and the light is on. And then I'm using the switches to simulate axles leaving and then go back to the previous state. So it's not very visual. You will see more on the next section. And then this is for the software simulation. So it's next item menus. And here we just compile. So we compile one replica of the application. It's verbose. You have a lot of things, and you get a picture when you have here on the right. You have the values of the variables in your model, and you can activate the switches as the inputs. So you can see the counter equal to 3, 4. And to have the axles leaving the trains, counter to 1, and you're back to the previous step. So the model is this one. So I just put the two parts of the model side by side. The project is available on the GitHub. So it's located on src xing underscore sky0.arc. It's an archive. And so if you want to get it back and to use it into your own environment, you use the menu workspace restore project. And you can see that everything was proved. You have the number of proof obligation and this is it. And then not the last but one action item. So I remember when I was demonstrating the board, I think the first time it was in Quebec, in Canada, someone asked me, well, it's okay, this is a safety computer, but how can I demonstrate that it is really safe? And it's difficult because it's supposed to react to very rare events. So you need to program it to be able to demonstrate this behavior. So we have three triggers. I will show two of these. So you can have a very long computation. So on this, the version for education, every 50 milliseconds maximum, the two microcontrollers have to exchange the message. Just saying, I'm safe, are you sure? Checking CLCs and so on. If you are doing a very long computation, one of the microcontroller will miss the rendezvous. And in this case, so the board will go in what we call in panic mode, meaning I blink, I just deactivate the output. You can use also an invalid value for the output. So this is what I said previously. If you are using a value different from IO off, IO on, and you can, so it was an addition because I think in this case it's more evident to show that you demonstrate this behavior. We have some built-in functions that call get replica ID and get processor ID, meaning that you can specialize the behavior of your software and to trick it, in fact, because in this case you will generate different behaviors depending on which replica is being executed. And at the moment, it only works with the board because on the software emulator, only execute one replica. Is difficult to simulate the fact that the two replicas are doing different things. And so I have a video for this. Is it? Yeah, it is. Yeah. Okay, so we start with the long computation. So you have the code on the right. And in fact, it's programmed in case the counter is greater than 8. So I just manipulate 8 times. And in this case, it goes passing a very long table, and you will see, yeah, I reach the counter 9, and you can see the blinking LEDs, meaning that it's a panic mode. The only way to get out is to remove energy and to restart. And the same thing here. So I'm using the get replica idea. So a different trick. I just use the living axle and just simulated the same thing. Okay, so just demonstrate that you can use different ways for demonstrating this safety thing. No, not this one. Too many slides. Sorry. So if you want to go further, so you have this document that was edited 2 years ago. So you have a description of the programming model. You have a description of the software and hardware interfaces. You have some examples that are going to be enriched this year. So what is really interesting is that you can use the boards in combinations. So you can have montage with things that outputs going to add the inputs to other boards. So we played with the R&D project for what we call a remote I/O system, so collecting I/Os from other equipments, or we can stimulate inputs, outputs with an Arduino and to check the behavior of a system. And just last two slides before going for industry. So I told you what moment that we can use B0 for the internal representation, and we could connect a DSL through a dedicated translator to the toolchain and to the platform. And so we did what we call a proof of concept for the French railways, and the idea is to transform some legacy system, very old system with so there is no electronics, it's just wires, relays, so it's basically electricity. We had printing drawings as inputs, and the idea is through some manual interaction to be able to generate B0 and to execute the wire logic on modern equipment. and I have a video for this. Okay, so the drawing is handwritten, but this is a real drawing. So you can see that we have an editor where we can superpose graphical elements, and these elements are then translated into B for electrical networks. Something more complicated with you can see a signal, railway signal, and then when it's translated into B0, it could be generated as the binaries and uploaded on the board. So we made some experiment with a 3D printer. Thank you, Patrick. And we can play with the signal, and we can go back to the drawing and check that the behavior is what we expect to be.